This is the lecture for Thursday, September 20th. We are going to talk about rotational motion, things going around in a circle, uniform circular motion, centripetal acceleration, radial component of the acceleration, which will be centripetal acceleration, and tangential acceleration. So let's get started. First topic is, the overarching theme is rotational motion. Okay, so we're going to think about rotation about a fixed axis. Something spinning around a fixed axis. Okay, but we're going to relate this to a particle going around a circle. Consider a particle going around a circle with radius capital R. Okay. So we have the circle, the particle here. The radius of the circle is R, capital R, and the angle that it's currently making with the positive x-axis is theta. Now, I want to talk about this segment of the circle, this what's called the arc length, how long that curved segment is. Let's call that S. Okay, so let theta be the angle counterclockwise from the positive x-axis. So in this discussion, theta will be measured in radians. The reason is that radians is more useful for connecting the arc length to the angle than degrees. So remember, 2 pi radians is equal to 360 degrees, or pi radians is equal to 180 degrees. Okay, I should mention, sometimes I'll write RAD for radians. Sometimes I won't bother writing RAD at all, I just write it like 2 pi. The reason is that radians, similar to degrees, really doesn't have a real unit. It's just a measure of an angle, how big an angle is. It's not something in meters or seconds or anything. So I'll write radians when I want to try to emphasize it's in radians, but otherwise it will not appear. Okay. Now there's a very simple formula from high school geometry relating the arc length to this arc length here, S, to the angle in radians and the radius. Then the arc length, meaning how long is this curved segment, this S is equal to capital R, the radius, times, let's just say radius, times the angle in radians. This does not work if you measure in degrees, so that's why we're doing radians here. Okay, now let's consider a change in the angle theta. Consider an angular displacement. Angular displacement. Delta theta during time interval delta t. The average angular velocity is, and I'm going to use this notation. This is this symbol is a small omega. Okay, the Greek letter omega. If you're wondering what the capital symbol for omega is, by the way, it looks like this. That's for capital omega, but this is the small omega. I've taught courses like this enough times that I know a lot of students like to memorize this or think of this as a W because it looks like a W. That's fine, but just realize it's actually called omega. So, but we're talking about the average angular velocity, so I can write AVG, or let's just put a bar above to tell us that it's average. So the average angular velocity is delta theta over delta t. Okay, this is supposed to remind you of V average is equal to delta x over delta t. But now we're talking about angles. So this will have units of, if you want to keep track of radians, it will be radians per second. Or if you don't want to keep track of the radians and just forget about radians, they'll just be the seconds coming from the delta t. So we'll just switch back and forth. The radians will come and go as we want, since it's not a real unit. The instantaneous angular velocity is omega without the bar, without the average. The limit as delta t goes to 0 of delta theta over delta t. And this is just the time derivative of theta with respect to t. And again, this has units of radians per second, or just inverse seconds if you prefer. All right, so this should not be too difficult to see the connection between instantaneous angular velocity and the instantaneous velocity we did before. The thing we did before is straight line velocity or linear velocity. So we had v is equal to dx dt. Now we're talking about angular velocity, instantaneous angular velocity. Omega is d theta dt. Now we'll consider a change in angular velocity. Delta omega during time interval delta t. Since the angular velocity is changing, now we can talk about the average angular acceleration. The average angular acceleration is alpha bar, so that's small capital alpha. Sorry, small. It's small, not capital alpha. The capitalized alpha looks like the letter A. Okay, so alpha, and that's delta omega over delta t. And this has units, because omega has units of radians per second, this becomes radians per second squared. Or if you don't want to keep track of radians, 1 over second squared. We can then talk about the instantaneous angular acceleration. And the instantaneous angular acceleration is alpha without the average sign, without the bar. And this will be alpha is equal to limit as delta t goes to 0, delta omega over delta t, or the time derivative of the angular velocity. If you have any questions about this or any of the stuff we've just covered, please ask questions to the student who's supervising the lecture today. Now, to keep track of all of these things we just said, I like to think about a linear, what we did before, linear to angular correspondence. All right, this is just to try to help keep things straight in your mind. What we did before, comparing to the new stuff we're doing with the rotational motion. So we have linear or straight line stuff over here, and then we have the angular new stuff over here, the rotational motion. So let's talk about position. Okay, so position, we say it was x, and this has units of meters. Then we have an angle theta, and this has units of radians, or if you don't want to write the radians, just 1. Then we have velocity. For velocity, that was v, and that is units of meters per second. Now, to do the angular case, we just take the Greek letter that goes with that, so it's omega, and that's 1/seconds, or if you want, you can put the radians in, radians per second. Now, for the acceleration, we have a, that's meters per second squared, and then we have over here angular acceleration, and that has units 1/second squared, or radians per second squared. Okay, the reason I'm doing this linear angular correspondence is now we can just replace all the x's by thetas, v's by omegas, a's by alphas, and we have the kinematic equations for constant angular acceleration. So these are the kinematic equations for constant angular acceleration. Okay, so what we had before with linear or constant a, and then angular. This is when you have constant angular acceleration, which we called alpha. Okay, so the reason I'm doing this is because I think it's the easiest way to learn this stuff. You just connect it to things very simply, to things you already know. So we have, for example, the final velocity is equal to the initial velocity plus a times delta t. If we change this to the angular case, the omega is the final angular velocity, omega 0 is the initial angular velocity, plus instead of the acceleration we have alpha for the angular acceleration. Delta t will just remain delta t. If we have something like x minus x0 is equal to 1/2 a delta t squared plus v0 delta t. Over here we would have theta minus theta 0, or if you want, in my notes I read this is delta x, or this is delta theta. And then you have 1/2 alpha delta t squared plus initial angular velocity times delta t, omega naught times delta t. We also have this formula v squared, v final squared minus v initial squared, or v0 squared, is equal to 2 times a, the acceleration, times x minus x0, or delta x. Over here we have final angular velocity squared minus initial angular velocity squared is equal to 2 times the angular acceleration, just replacing things, times theta, final position minus the initial position, or if you want to write this as delta theta. If we have a formula like the average angular velocity over an interval happens to be the average value of the initial and the final velocity. Same thing here. The average value of the angular velocity in an interval is 1/2 the sum of the initial and the final angular velocities. So if you just look things up this way, you don't have to relearn anything. You can just you can solve constant acceleration, angular acceleration problems. You can solve constant angular acceleration problems much the same way as constant acceleration problems. Okay. If you have any questions about this, please ask the stream supervisor in today's lecture. Let's solidify this with an example. Okay, let's say the seconds hand on a watch starts with proper speed. So this is an old-fashioned analog watch. So remember, the seconds hands on a watch goes around one time, one revolution per minute. That's what a second hand is supposed to do. Okay, so it starts with the proper speed, angular speed if you want, but then slows to a stop uniformly. By uniformly, I mean constant angular acceleration over a period of 1 day. The question is, what is the value of the average angular? What is the value of the angular acceleration? It's a constant angular acceleration. And the second part is how many radians does the second hand, rotate. Okay. Before I go over the solution, I will stop the video, and you can give it a try yourself first.